But we'll try to have like an actual dead week. Does that sound good? Hey, Brandon, sorry about that. I just accidentally clicked out of the meeting for some reason. Okay. Oh, it's still live streaming? I guess it's still live streaming. Okay. I don't know what I did. All right. So let's do the division algorithm. But yeah, I'm pretty sure what we decided on was that we just do some more from section 4.1 on the last homework. So there's just one more homework on dead week. It's just more of the same stuff. Okay, so here it is. So theorem 4.6, the division algorithm in F adjoin X. Okay, so we're going to start with two polynomials, and we're going to say that g of x is non-zero. Why do you think we'll need that?
You're going to basically divide by it.
Yeah, we're kind of dividing by g is the idea. So g is going to be our divisor. Okay. Then there exist unique polynomials. Q of x and R of x. Such that, and we know what it's going to say, don't we? So f of x equals, what do you think? G of x, oops, that's a q. G of x, q of x plus r of x. Right. Can you tell the difference in my g's and q's? They kind of look the same. G of x, q of x plus r of x. And now, what do we say about the r of x? Remember in integers, we said that like somehow r has some bounds on it, right? So how might we bound it here? What do you think would make sense? Yeah, so if we just did it straight, it would be something like this. Less than which one? G of x. But what does that even mean, right? What does that even mean here? Colin, do you have that?
Would we need the constraint that it's less than f of x? Because it would have to, because we're oh well, maybe not, if it like cancels.
Okay, so let's pause for a minute and we want to fill in what this constraint needs to be. William, yeah.
I was just going to say, like, if the degree of f of x, or sorry, g of x, like g of x times q of x has to be the degree of f of x, and r of x can't be bigger than the degree G.
Yes, that's actually the condition. Yes, so good. So we need that the degree, so actually there are two conditions. Either the remainder is 0 or the remainder's degree is less than the degree of g of x. Yeah, so where or the degree of r of x. Okay, so that's the idea. So we're restricting, so what does it mean to say R is within this bound? Really, we're going to be talking about the degree. Yeah. Good. Okay, so remember polynomial long division? We're going to do some of that today. So, we're going to divide. Okay, we're going to divide. We're going to divide f of x, which is equal to 3x to the 5th plus 2x to the 4th plus 2x cubed plus 4x squared plus x minus 2 by g of x, oops, that's not the b, g of x, which is equal to 2x cubed plus 1. All right. So if you remember doing this, put your division symbol here. So we've got 3x to the 5th plus 2x to the 4th. Those of you that work in the MLSC are going to be up to par on this, right? You've probably done this a lot with students. Have you? Have you done? No? Okay. Have you done it some with students, Julie? No?
I think they're all done like synthetic division.
Yeah, they
Which is
just.
like, because like the thing they need to do this in the other direction for their like.
Yeah, I hate synthetic division because I think it's like strips it of all meaning completely. And you're just, it's the same thing, but you're just fiddling with the coefficients essentially.
Is
So-
synthetic division just the same thing as like solving for the coefficient, like you write down the term, and it's just solve for coefficients.
Yes. Uh-huh.
Yeah, that makes
Yeah.
the code, just solving the coefficients makes much more sense to me.
Yeah, but but for the students, I think they have no idea what they're doing. They have no idea what they're doing. So it's it's kind of terrible. As much as I hate polynomial long division, I think it is more meaningful somehow. Even though it is still a procedure, so maybe it's not the best thing either. I don't know. I don't have the solution, but anyway, so we want to divide that by 2x cubed. So we have, so I'm going to write it as 2x cubed plus 0x squared plus 0x plus 1, just for some placeholders. I think it'll help us in our computation. Okay, so what can I multiply 2x cubed by to get 3x to the 5th? Yeah, 3 times x squared. Good. Like we definitely need an x squared, then we need to make the coefficients work out, right? So 3 times x squared, perfect. So we're going to multiply that by each of these guys and put the result below here. So 3 times x squared by multiplied by 2x cubed. Well, that's going to give me 3x to the 5th. That's how I got that number in the first place, right? We manufactured that to work out. Then I'm going to multiply that by 0x squared. I'm going to get 0x to the 4th plus that times 0x is going to give me 0x cubed. That times 1 is going to give me 3 halves x squared. And then I want to subtract all of that off. Okay, so the first term goes away, and then I'm left with this 2x to the 4th is going to drop down. 2x cubed minus 0x cubed is 2x cubed. 4x squared minus 3 halves x squared. Let's see, that's 8 halves minus 3 halves. I've got 5 halves x squared. There, right? And I'm going to drop down the plus x. and do it again. Do we need the -2? Yes. Maybe. I think we'll drop that down next time. Yeah. Do that next time. Okay. I mean, I guess if you want to have it there, we can just drop. Yeah, it doesn't matter either way. Okay, so what do I need to multiply 2x cubed by to get 2x to the fourth? That's an easy one. Plus x, perfect. So we'll do that, 2x to the fourth. Plus 0x cubed plus 0x squared plus x. I'll subtract that all off. And so 2x to the fourth minus 2x to the fourth, we'll have 2x cubed plus 5 has x squared plus 0x minus 2. Okay. And this is the last time we can do something. So what do I need to multiply 2x cubed by to get 2x cubed? Just 1. And so we'll multiply that all over. So I get 2x cubed plus 0x squared plus 0x plus 1. And I want to subtract that off. So that part will go away. I'll have 5 halves x squared. Negative -2 minus 1, so -3. Okay. And so, so if we take a look at our remainder, this is our remainder. So our r of x is 5 halves x squared minus 3. So our remainder is not 0, right? But what is the degree of our remainder? Degree 2, and we want to compare that to the degree of what? G of x. And so is the degree of this one less than the degree of g of x? Yes, because our remainder is in the right, it satisfies those conditions. So what I can write is I can write that I can say f of x equals g of x cube x plus r of x. Right? And so I can write that out, and I can write whatever all that is. So I can say 3x to the fifth, oh gosh, plus 2x to the fourth, plus 2x cubed, plus 4x squared, plus x minus 2 is equal to this times that, right? So 2x cubed plus 1 multiplied by 3 halves x squared plus x plus 1 plus my remainder. So that's what we get from the division algorithm. And the division algorithm tells us that those are unique, right? Those are unique polynomials. Okay, question?
Does it mean anything that this kind of feels like if you just had x equals 10, this would be like doing it digit by digit for like regular integers?
Yes. Yes, it is. So, but the issue with that is if x equals 10, like these, like, so the difference would be like these, that could be something greater than 9.
Right, so it'd be like improper base. Yeah.
And kind of improper a little bit, but yeah, as if you restrict your, what I'm trying to say, coefficients to be integers between 0 and 9, then yes, it's analogous.
So how close could you, if you just wanted to prove this in like a modulus or something, how close could you get to doing it sort of like the
same original proof? Yeah, and so the proof in the book is kind of interesting. I like what it does in that it follows this example that we just did. And so if you look, so it's kind of cool because it has the example we just did side by side with the proof. And it's kind of showing how the proof and this long division kind of go hand in hand. So the proof is kind of following the process of the long division. And so in the like math education literature, we would call this like a generic example. So it's an example, but the proof follows the same structure as the example. Which is, so it's kind of a neat side by side there if you check that out in the textbook. So yeah, so I think you're exactly right, Colin.
Yeah, that is cool. I feel like I noticed when we were doing the original division algorithm, it seemed like the proof, like it didn't seem obvious to me if it was similar to this kind of dividing. Is there a reason that one seemed to be?
Well, so that proof used the well ordering axiom, right? And so I feel like when you use the well ordering axiom, it feels a little like magic, every time. So so it's maybe not as intuitive. So yeah, I'm skipping the proof today because I just want to do some examples. But yeah, but I would encourage you to read it, just kind of read the side-by-side proof with the example. It's kind of interesting. I think it does the uniqueness separate. I didn't prep for it because I was like, I was going to skip it, so I didn't really read it super carefully. Yeah, so the uniqueness is kind of separate from the example, which we saw before. It's kind of like you get the Q and R, and then you've got to prove uniqueness kind of separately. So it does the side by side with the example to like find the Q and the R, and then the uniqueness is like its own little paragraph. Okay, so anyway, so you can check that out. Let's do some. I'm gonna get you all to do some stuff. So I'm gonna give you. This is close to one of the homework problems. I think I assigned parts B and C, so let's do A and D in class. Okay, and I'll just have you all work on this in groups a little bit. So we're gonna do some division algorithm in different rings. Okay, so and kind of see how that works out. So this is 4.1.5 part A, and then we'll do part D as well. So 4.1.5 part A. So we're going to find polynomials, Q of X and R of X, such that F of X equals G of X, Q of X plus R of X. And either R of X equals 0 or the degree of X. So we're just finding the Q and R from the division algorithm. So we're going to do. So the first one gives you that F of X is equal to 3x to the 4th minus 2x cubed plus 6x squared minus x plus 2. And my G of X is going to be x squared plus x plus 1. And my ring is Q of X, Q adjoint X. Okay, and then the next one is going to be, we have our F of X equals 4x to the 4th plus 2x cubed plus 6x squared plus 4x plus 5. And our G of X is going to be 3x squared plus 2. And our ring here is Z mod 7 adjoint X. All right. So I'm just going to let y'all work on that for a little bit, and then we'll do it together when you all get done. So we'll take maybe 5 or 6 minutes to get started on this and work with your groups if you can. I asked him, all I said that you texted her about the, she got it fixed. Okay, thanks.
It's because there's like a power button on the phone.
Yes, yeah. Which is weird that someone turned it off anyway. Usually we leave it on during the week. Yeah, I had to call IT to find the power button the first time. Right? Let's see. Does being in the ring Q of X come up at all in this? I'm wondering. Not really, does it seem to?
So yeah, so you have to check on the 7
In this neighborhood, when she started it all, yeah, I was a feminist person, so like, yes, and you tweeted it out, yeah.
Okay, am I getting what y'all are getting? Yeah. Yes.
You got it.
Okay, I got my remainder to be -4x - 6. That seemed like what y'all got? Okay. So it seemed like being in the ring Q of X didn't really impact this. I mean, it was almost like being in R of X here, right? So maybe this other one being in Z mod 7 to join X. Have you started that one or you just? So we'll write down our Q of X.
I was doing this.
Brandon, Jose, how's it coming?
It's coming along.
Coming along, okay.
Oh, yeah. It actually is.
So I'm curious about this It makes me wonder if we could just do it the same as if we were in like R join X and then take the answer mod 7, or if you have to kind of like consider the mod 7 all along.
Kind of, we had to,
Yeah.
like, you run into 4/3 right away.
Uh-huh.
But if you, like, what you
So
actually
you have to
want is
solve that equation.
you want to solve 3x is congruent to 4 mod 7.
Mm-hmm.
So you can just like do, well, 7 is prime, so we can divide.
Yeah.
So you did like 3x is congruent to 18 mod 7 and then you did 6.
Yeah.
Which looks weird, but
It works.
works.
Yeah. It's like almost like I need a multiplication table mod 7 over here to reference, right? So maybe I'll make one real quick. Let's see. Three times 3 is 9.
So how do you, on the notation on this, would you just like, when you write out the full polynomial, so congruent, or you kind of 4x to the fourth, plus 2x plus 6, 4x plus 5 is congruent to g cubed plus r.
Wait, I shouldn't have that. Everything's a unit, so I've got to hit every number. I messed up my multiplication. So 2 times 4 is 8. Wait. 2 times 4 is 8, which is 1 mod 7. Oh, okay. 2 times 5 is 10, which is that's better.
So on the second one,
4 times 5 is
so you had, I could do these like, you get 4/3, you know? Oh, yeah, that's it. Yeah. So I did the same thing you did, so I think. I'm not sure about this. Something like that. I'm not sure about that. Dr. No?
Did I mess up my multiplication table? Oh.
Yeah, I did too.
You got what?
Oh, I was just gonna ask, okay, if we were to write out that equation with the polynomials, do we say, would we say that like f of x is congruent to GQ plus R
Yeah, that's what I got.
mod 7?
I think we'll just use equal to, and we'll just understand that our ring is the mod 7.
Okay,
So they're equal in that ring, which means the coefficients are congruent. Right?
oh, they would be equal in.
In this ring, right? And what equal in that
Oh, so
ring,
it's like a
what equal in that ring means is that the coefficient, the corresponding coefficients are in the same congruence class. Right?
Oh, okay.
Yeah. Okay, so all right, so right off the bat, we're gonna have to divide, right? So so what do we get here for this
6.
So 6, because 6 times 3, if I look at my multiplication table, 6 times 3 is 4, right? So, so I get a 4 there. 6 times 0 is 0. And 6 times 2 is 4, right? Agreed? Yes? No? Yes? Okay. Okay, and so then we get 0, we get 2x cubed, and we get 6 minus 4 is 2. Did I mess up?
6 times 2 is 5.
6 times
2 is 5.
2. is 5. Yes, okay, thank you. So then 6 minus 5 is just x squared. Okay, perfect. All right, then what do I need to do? I need to get a 2. 3 times something is 2. So 3 times 3 is 2. Yeah. Okay, so we'll do a 3x. So 3x times 3x squared is, this is kind of fun, huh? Oh, so 3 times 3 is 3 times 2 is 2, obviously, because that's what I just did. 3 times 0 is 0. 3 times 2 is 6. Okay, then I'm gonna subtract that. Okay, so 4 minus 6 is -2, which is 5. Yeah.
We just left it negative.
Oh, yeah, that's fine too. Yeah, I mean, well, it's all congruent, right? And then x squared. So x squared plus 5x plus 5. And then I just need what? I need something times 3 is 1. It looks like 3 times 5 is 1, right?
Mhm.
So you do a, is everyone following this or is this too much? So we just need a, okay,
Plus
now,
5.
a 5?
Yes.
Okay, so 3 times 5 is 1, x squared. 5 times 0 is 0. 5 times 2 is 3. My multiplication table helped a lot, actually. Did you all make one?
No.
No? Yeah, that helped. That helped a lot. Okay, subtract that off. I was sitting there doing that, like, is this worth my time? But I think it was, actually,
Mhm.
in that case. So you're subtracting this off. I get 5x, and then 5 minus 3 is 2. 5x plus 2. It's not gonna make it.
Yeah, we did -2x plus 2, but that would be congruent.
Yes, that would be
So-
congruent. Yeah, -2x plus 2 is congruent. Yeah. Oh, crap. That's gonna make it hard to grade. Okay.
Was it like a good rule of thumb to always have positives, or does it matter?
Oh, it doesn't matter. I mean, I can figure it out, but anyway. I always like to write it as positives just because it feels more complete. I don't know, but if it's congruent, it's fine. Yeah.
Wasn't it latexing this? Is it okay to just write like dot? It's
Oh my gosh, are you gonna try LaTeX long division?
Yeah, I
Holy crap, I don't even know how to. You could just not LaTeX the long division and it'll be fine.
Just
Just
put
look at
the-
your bonus points.
Okay.
Oh, I wasn't even thinking about that. Yeah, I mean, unless you just really want to learn how to do it, I don't think I would do that. Colin?
I was just gonna say, can I say real quick one more time that Desmos, the graphing calculator, the stuff you type in there is secretly LaTeX, and if you copy and paste it, it
Oh.
turns up as LaTeX code. So if you need like massive stuff,
Will it do long division in that sense?
I don't know about the long division notation, but it helps with the polynomials because you can just type those out.
Type them out, yeah, that's
Nice.
true. Yeah.
On that second line of subtraction, when we subtract 6x from 4x,
Oh, did I mess up?
would it become -2x there? Can you explain that?
Yeah, so what is -2 congruent to mod 7?
Oh, I see.
Yes. So
So-
negative, yeah.
We can't have negatives then?
Oh, you can.
Oh, it's, oh.
Yeah, I was just discussing that I feel like positives, like, I don't know, it makes me feel better.
Like on homework or like the test, -2 wouldn't work. then?
Oh, yeah, for sure, it's congruent. Yeah, any other questions? Okay, then let's do teaching evaluations and be done, so, I'm gonna make sure y'all have some more time. Okay, so I think you need information about me. I'll write this like my name and our CRN up here. And
I haven't been in the room, so sometimes we just kind of rely
This is whatever, it's taking so long, so I just wrote it and attached it.
Which one?
The, from a couple homeworks ago, that was.
Oh,
the
And I think they like it all, but.
It's taking so long, I'm sure my hand and attached it.
Yeah, have you seen, I don't, like, nobody uses.
Okay,
it.
online
It's like-
people, sorry you don't get to do teaching